So Dr. Rajagopalan completed his clinical and research fellowships in cardiovascular medicine and vascular biology at Emory University. After leadership experiences at Ohio State and Maryland, Sanjay joined the UH family in 2015. His research focuses on determining the mechanisms by which environment triggers predispose to adverse cardiovascular risk factors and other medical sequelae. Today, Sanjay will speak about the environment impact on cardiovascular health. Sanjay.
Thank you, Mukesh, and it's really a pleasure and honor to be here today and to join you at this very distinguished, august conference, and particular thanks to all of the folks that made this conference possible, and obviously to Dr. Agre to be here today. So I'll start with the provocative notion. I think David did a great job presenting sort of how simple tests can inform you about potential treatment options and help you even stratify risk in patient population. And this is a very interesting quote on problems. Problems cannot be solved with the current level of consciousness that created them. And we are now at the midst of an epidemic, not only of infectious disease pandemic, and an epidemic of cardiovascular disease. And my sort of humble sentiment at the beginning of this talk is just to apply this logic to you and to say that, in order to make further advances in cardiovascular disease, we really need to step up consciousness by which we approach these problems. So my talk is on convergent connected cardiovascular health through environmental transformation, and I hope to touch upon some of these aspects that I just alluded to. We are right now in the middle of what is arguably a massive industrial convergence, where disruptive innovation is forcing links across not just technologies, but entire industry sectors. This convergence is happening not only in, obviously, the industries that you see in front of you, but also in the medical world, where seismic forces are shaping the way data is generated, integrated, and collapsed to diagnose and treat patients. And David presented some of these approaches in his talk. Now, there are two concepts in a convergence nodal framework that are worth highlighting. The first is the concept of connectedness, so connected cascading risks, which is particularly relevant to environmental disasters, where disruption of even a single node, not directly connected to other nodes, can cause unintended consequences. And you're all well aware of this. This is exemplified by the COVID-19 pandemic, where a series of seemingly disconnected events led to an international catastrophe, connected economic phenomena that lead to recessions, and the mother of connected cascading risks, climate change, also recognizing that these events themselves are connected. So my submission is science may not solve the big problems facing us, like climate change, which is going to take a whole lot of politics and political convergence of a different level altogether in a global way. And you might recognize these two individuals, Jeffrey Rose and Rudolf Virchow. And Jeffrey Rose famously said, the primary determinants of disease are economic and social, and therefore medicine and politics cannot be kept apart. When you talk about the environment, and in this slide I'm just discussing the physical environment, they're often unrecognized contributors to global morbidity and mortality. The Lancet Commission on Pollution and Health, and this is data taken from the very important paper, obviously from the Lancet, that we abstracted for this review in the Journal of American College of Cardiology, estimated that roughly 9.1 million deaths were directly attributable to known pollutants, and this is just the tip of the iceberg. And this is the first large-scale catalog, if you will, of global attributable deaths to environmental causes that was ever performed. Air pollution, considered within this construct, is the fourth leading cause of mortality, with more than 6 million lives, depending on how you do the math, and some estimates more recently attribute roughly 9 to 12 million deaths annually just to air pollution alone. This is, and again, this is no offense to my colleagues, obviously studying tuberculosis and malaria or HIV. This is 3 times more than the total deaths due to TB, AIDS, and malaria combined, and more than 15-fold higher than all wars and violence combined. So now I would like you to do a thought experiment where if you were to turn off at one swoop all fossil fuel emissions, let's say you went all electric cars and changed your energy consumption to natural sources, then in any given year, the START experiment was published a few years ago, you can save roughly 3.61 million lives, and this is just fossil fuel emissions. Now, if you were to turn off all anthropogenic pollution, a lot of other sources that contribute to climate change and to emissions, particulate matter, gaseous pollutants, then you'd wind up saving roughly 5.5 million lives annually. Now, there are also other aspects of the environment that are almost ubiquitous, and we don't normally stop to pay attention to this. Light pollution, which is a well-known circadian disruptor, is also known to be associated with effects on cardiovascular health, cardiovascular mortality, and this is a review that we just did a year ago, published in 2021, wrote up last year. And just like air pollution, noise pollution also has a number of consequences in cardiovascular health. So these three factors that are so ubiquitous in your environment can have profound effects on cardiovascular morbidity and mortality. Now, what about the social environment? In this very interesting study published by Sudhir Alkindi, one junior faculty member that David mentioned in his talk, what Sudhir did was to take all of the deaths annually from zip code level data. There's 5,769,000 deaths in 3,106 US counties, put these deaths all together, and also looked at what's called a social deprivation index, which is a measure of vulnerability at the community level. It was initially generated by the CDC, but it's often widely used to identify susceptible communities defined by the neighborhoods that they live, income, other socioeconomic variables. There are 4 different domains and 15 different variables. So these maps, these heat maps, provide you a very stark contrast of the gradations that you see when you examine mortality. You can see red in the American South, and just concordant with this are PM 2.5 level, which is a measure of particulate air pollution, and you can see, you can almost juxtapose these images. And when you look at social deprivation index, you'll see that there's some level of concordance between these areas, obviously a lot more red that you see across the US. So when you start to look at quartiles of social determinant index, or SDI, and the higher the index, the higher the social deprivation, or SDIs of 51 to 75 is a higher level of vulnerability. And you plot on the x-axis PM 2.5 levels, or levels of air pollution, you see that this gets a lot better at higher levels of social vulnerability. So when you throw in a measure of social vulnerability on top of an environmental determinant, you can actually start to see very interesting relationships between cardiovascular mortality, shown here age-adjusted cardiovascular mortality is on the y-axis, and complex socio-environmic variables. And I truly believe that this starts to get at the issue of other unknown determinants of cardiovascular morbidity and mortality, and this is, the next generation of work that needs to be done. We also know a whole lot about the internal environment, a multitude of factors, highly complex. We're just scratching the surface. Suffice to say, the negative health behaviors and psychosocial risk factors markedly increase the risk for cardiovascular death and myocardial infarction, often in a very cascading fashion, very reminiscent of the environmental cascading risk that I spoke to you about. And this is a very recent, well-done paper that goes to demonstrate genetic underpinnings and how sleep which itself is genetically determined, at least the way you sleep and how often you wake up. And when you put this together with underlying cardiovascular risk, you start to see some very interesting patterns. So this was a Mendelian randomization study where what they did was they determined 68 single nucleotide polymorphisms from the cardiogram plus CAD cohort, which is, as you know, is a very large cohort where they did GWAS studies and they figured out these SNPs that are associated with higher risk for cardiovascular death. And what they did was they assigned patients in the UK Biobank, which is, as you know, a very well phenotyped patient population of roughly 500,000 individuals living in the UK who have sleep information. And they looked at the interaction between cardiovascular risk defined genetically with sleep duration. And the comparator group here is low genetic risk and favorable sleep duration. And when you add these components together, in other words, you add unfavorable sleep duration to, let's say, low genetic risk, you start to see a pattern where the highest risk individual is those who have an underlying genetic predisposition for cardiovascular risk and an unfavorable sleep duration, where you see a hazard ratio of roughly 2.4 for a future myocardial infarction. So these are just initial attempts at starting to understand the very complex interplay of how the internal environment might conspire with the genetics. And again, we haven't taken into account the external environment here, but these are the types of approaches I truly believe will inform us as we move forward into a brave new world of multi-omics data sets. And here's a very interesting neurobiological model that's hopefully somewhat of a composite model that puts into in a graphical format how might external stimuli influence the internal environment and activate mechanisms of inflammation. So you can see stress, and this could be a variety of different stresses. It could be noise, it could be air pollution, it could be depression. This activates components in the brain, especially in the limbic system. The prototypical organ is obviously the amygdala. Amygdala activation results in efferent output to the brainstem, where you activate sympathetic nervous system circuits. There's downregulation of parasympathetic axis, and the sympathetics, as you know, is very wired to the bone marrow, where it might elucidate a pro-inflammatory response in the bone marrow. You see an activated immune axis, and these cells magically know where they need to go by virtue of chemokine receptors and other honing signals, where they gravitate towards vascular beds as well as the heart in order to affect deleterious cardiovascular consequences. So it's a very surprisingly consistent model that works across a variety of different stresses. The other convergent mechanism that obviously got the individual a Nobel Prize, like Dr. Agre, is the circadian system, where disruptors of the circadian system is very well known to disrupt a whole range of different cascades that might be maladaptive and predispose one to cardiovascular health. The prototypical example, obviously, is disruption of sleep as a circadian disruptor. And you know, I've already talked to you about sleep, but there could be other environmental triggers as well that could activate or rather disrupt circadian rhythm in order to cause problems. So in the last 3 minutes, I'll give you some insights into this. We conducted an experiment where we compared light as a classical circadian disruptor with air pollution. The slides are a little bit hard to read, but essentially what we did was to expose animals to high levels of air pollution over nearly 30 weeks, which is a fairly long duration. And these mice, like we've shown before, develop insulin resistance, and as shown here by the insulin tolerance curves. The PM2.5 obviously refers to pollution, whereas the LD refers to a mouse that was with a normal circadian rhythm of light during the day and dark at night, whereas LL is light exposure both during the day as well as at night. And this slide, again, is a little hard to read, but what this slide hopefully conveys to you is a markedly different circadian rhythm in response to not only light exposure, but also air pollution exposure, not only in the liver, but also in the brown adipose tissue. And this in turn translates into very obvious abnormalities in metabolism, where you see a reduction in VO2 max as well as VCO2 in response to not only air pollution, but also light. But what was very different is the type of transcriptional changes that you see in response to light, which is quite different from what you see in response to another environmental trigger, PM2.5. And in this slide, it's a little complex again, I apologize for this. This is ATAC-seq data looking at chromatin dynamics, or the openness of regulatory regions in the chromosome. And this is looking at 21,000 protein encoding genes. The slide on the left, or the graphic on the left in red, which is a histogram. And the wider the red is obviously the more open promoter regions in the chromatin. And you can see PM2.5 facilitates an open chromatin environment. The middle slide here shows in magenta depicts just the circadian genes, the top 10% circadian genes and how they are regulated. And again, it looks at the promoter openness, and you can see much more darker magenta in response to PM2.5. But this pattern is very different than what you see with light exposure. And again, the bar graphs again illustrate various regions, including the promoters as well as enhancer elements, a quite different effect of air pollution versus that of light. So the bottom line is we see a very different circadian disruption pattern, very different set of genes that are regulated, but not only that, different regions of the chromosome. And how this might be, we investigated this in this paper where we looked at potential pathways that could render the chromosome more open, such as histone deacetylases, and no differences in DNA methyltransferases, but clearly in response to air pollution exposure, there seemed to be a downregulation of HDAC2, HDAC3, and HDAC4 that could potentially be one putative pathway by which you could render the chromatin more open. We also looked at specific histone acetylase hat proteins, including P300, and again using CHIP, where we immunoprecipitated 2 circadian proteins, PER1 and PER2. We PCR'd 3 different hat mechanisms, P300, PCAF, and polymerase II, and you clearly see differences in response to PM2.5. In other words, there was increased levels of expression of these potential acetylated proteins that could represent one mechanism of rendering chromatin openness. So I'll stop here. Hopefully I've given you a little bit of insight into what it might take in the brave new world to approach cardiovascular disease, where we might need convergent connected solutions and a wide variety of different data streams in order to truly make an impact on cardiovascular disease. Stop here with acknowledging many of my collaborators and colleagues, and especially the postdocs who did most of the work. Thank you very much.
Well, thanks very much, Sanjay, for a really provocative talk. And it really makes you think. A lot of our talks today were internal, and you've taken us external and the environment and how it impacts us. We have a few questions, but maybe I can, the first one that came through, and I think it's a very logical extension of the comments you had towards the end, some of the data that you showed, which is you showed pollution causing changes and circadian disruption. Is that reversible? So that if we do, as you know, there's so much effort nationally to try to improve air quality. Will it have an impact? And will it reverse at the genetic level or the epigenetic level the changes that you see?
Great, thank you, Mukesh. Truly provocative question, and I think this is where we need to really understand the role of prevention. At least in one experiment where we look at transcriptional changes following cessation of air pollution, you see a reversal of some of the pathways. We do see some changes, a reversal of some of the epigenetic changes, but I think further work needs to be done in order to understand some of the epigenetic changes, because a big question is how permanent or enduring are some of these chromatin changes and whether these are reversible or not.
Yeah. Another question is, what is the value of convergent thinking in disease generally or broadly?
Well, as you know, I'm a big fan of it. I don't know exactly how to do it, but I certainly can do a talk on it. But I really think these additional data streams that we're getting in terms of not only multi-omics data sets at a molecular level, but also factoring in some of the environmental variables as well as some of the other disease variables that we get from very simple tests could really be powerful in terms of pushing the frontiers in terms of not only identifying risk, but also identifying candidates that might be most suited for certain therapies. And I think it can all be done quite easily now with machine learning approaches where you could really get to an individual level, but at the same time service a whole population.
Yeah. And let me see, I think we're okay. We can do another question or two. Let's see. How does one model climate change in the laboratory?
That's a tough one. Fortunately, it's difficult, and this is a big issue. But for all the reasons that our audience probably appreciates, it's very difficult to distill hundreds of years, thousands of years in a test tube. The best we can do is maybe get at some very, very immediate questions of relevance medically, like what the effects of high temperature are, for instance, or construct disease algorithms where you throw in a whole bunch of other variables in addition to heat stress and look at the adaptation. So I guess most of the questions in the laboratory, at least from my limited perspective, is to be able to address what the extremes, what the human response, disease response, rather the organism response is to extreme stress. That's the best I can do right now, but it's really hard to.
And can you, I suppose is there value, or would it just be too complicated to integrate different stresses? So, you talked about a whole bunch, and I don't know which one of these, but there's light, there's noise, there's temperature, there's air particulate.
Particles,
and are there individuals, your lab or others, who are studying this? Clearly it's being done at a population level, so there's data,
right.
But can it be in some way recapitulated in the laboratory so we can try to get at more mechanistic information?
Yes, I believe you can. I think it's helpful to really get at some dimensions of information that might be helpful to understand population level data.
Yeah.
But as you mentioned, I think putting together a multitude of these variables will help you understand the cumulative impact of some of these stressors and get you some additional insights.
All right. I think those are the questions, sir. Thank you, Sanjay.
Great.
That
Thank
was
you,
just
Mukesh. Appreciate
terrific.
it.